Okay, this next screen capture, we're looking at something different. We're taking the same frames of the model. In fact, it takes 5 days of data where our cruise or field trip day was the center of the 5 days, and then I do what's called low pass filter. Essentially I run a filter through the model and I take out the high frequency components, the tide frequency components. So things that are happening at twice a day frequencies are removed from the system. We're looking at longer term variability. We call this subtidal. Think of it simply as removing the effects of the tides. What happens when the tides are gone? What is still going on? So this subtidal, we're looking the same day, but this is the subtidal data. So let me just start from the beginning, and you'll see that it doesn't change much throughout the day compared to when the tides are action. So the tides, the tides are the dominant source of energy, stuff going on in our environment. But really the subtidal components are important because this affects things like larval dispersal. Otherwise, with the tide, you're just generally going back and forth and sort of ending where you started from. You might have had a journey, but you really didn't get anywhere. The subtidal component shows you that over the course of that, you may have also incurred some drift as well. For example, driven by winds or tidal asymmetries or interaction of tidal eddies, things like that can influence the dispersion. We're looking at the same thing again. This is this transect across Buzzards Bay, this black line like this. I've enlarged my mouse pointer, and we see again that the dotted lines again are up bay water velocity moving towards the northeast. The dashed lines are down bay moving towards the southwest. You'll see that throughout the day this pattern essentially just strengthens. There it's strengthening, so you have stronger up bay, stronger down bay. Our contours are crunching together. The colors are becoming more contrasted or in greater contrast. And then it starts to weaken again. So while we were on the water, it looked like roughly the strongest contrast or strongest shear in the subtidal sense occurred, at least in the model, at noon. So we were just coming back when that happened. That's because the wind was building. So what you see here is this essentially a circulation originally described by Shinati in the context of lakes, and maybe we'll have Miles mention something about it. To really understand it requires getting into understanding force balances. We haven't really discussed that in class. So I'll just note the important thing is that I'll just show you actually the forces at play. The wind moving on the surface out of the screen here in the same sense as these positive velocities. So where the wind is strong, the velocity is moving with the wind in the subtidal sense. And you have this line here dividing down bay surface water and up bay deep water. So there's essentially return flow. And you can think of it like an estuary in that sense. So there's two-way flow here, a downwind flow, down bay, downwind in this case, flow here, and the surface waters, and in the deeper waters, it's up bay. And this solution was originally described by Shinati, and you can look at it using a simple force balance. The forces at play, you have wind stress, bottom friction, and a pressure gradient. And so the pressure gradient in this part, I'm not talking about. So pressure gradient essentially means that the water in one location, say down here, is higher or lower than the water in this location here. And high water likes to push water towards low water. Think of water flowing downhill. And so we'll compute that numerically in a few weeks, but I just want to show you at this point the pressure gradient. I think I have it back here in the bay. This is subtidal. I've removed the effect of the tides. The tides create strong pressure gradients, and that's why the water moves around. If you erase them, this is what you're left with. This is a wind-driven pressure gradient, a local wind-driven pressure gradient. So here's the bay again. This black line here along the bay, along that line I'm looking at the free surface elevation, the height of the water above its mean value, above a zero. If everything was zero, you'd have everything be at the same level, and there's no pressure gradient. What we're seeing here is in the south end of the bay, or southwest end of the bay, the water's higher than it is in the down end of the bay. And that's a result of the water moving in this direction. The water's moving, I'm sorry, the wind. The wind is blowing from the right side of this graph to the left side of this graph. Associated with it is this water elevation. And what this water elevation is going to try to do is here, just thinking in simple terms, if we're a water parcel, so this is the mean depth of the water somewhere here. If I'm a water parcel at this level, at this mean level here, and if I'm a water parcel here, experiencing different pressures. I'm sitting here as a water parcel. I have this much water on top of my head, roughly 20 centimeters, something like that. So, actually 2. And we have, here we have less water. So the pressure here is higher than here. And if I'm a water parcel in the middle, I'm getting pushed from left to right. So the water wants to return back up bay. So the wind generates this pressure gradient, and the water wants to return back up bay. Now, what forces are we experiencing? If you're a water parcel at the surface, you're experiencing that pressure gradient that wants to return you up bay, but you're also experiencing the wind, which is going to pull you down bay. If you're in deeper water, you are not experiencing the wind so much, but you're still experiencing that same pressure gradient. So think of it in drastic terms. The surface is experiencing the wind dominates, it pushes in the direction of the wind, and at the bottom has no sense of the wind, the pressure gradient dominates, and the pressure wants to push it back up the bay. The pressure wins out. So you have this two-way flow. That was a somewhat drastic simplification, but you have this two-way flow set up, and what that means is you have a very strong exchange of water. I think that's what I'm trying to say, in these kind of embayments. So it's not as if the water is pushing all the water out of the bay or all the water into the bay. You have this two-way flow, and then this sort of exchange of surface water, and it's drawing in deep water from Rhode Island Sound is coming in to replace the surface water, which is getting pushed out the top. So this wind is driving an exchange of water. Now, most of the time in the summer, the winds are the opposite. It is a sea breeze. The sea breeze is southwest. It blows right up the bay. This is June, this is July, this is August, this is September, right up the bay. So it's the opposite picture in that sense. The surface currents are being pulled up the bay. The elevation is higher at the top of the bay, lower at the bottom of the bay, meaning the pressure gradient associated with the subtidal elevations wants to push water back down the bay. So the surface waters are going with the wind. The deep waters don't know about the wind. They only know about the pressure gradient, and so they're being pushed back down the bay. So in that case, you have surface water being drawn in from Rhode Island Sound and Buzzards Bay water exported to the deeper stretches into the bay. So this picture is reversed. The dash contours are in the surface, the solid contours are in the bottom during the southwest sea breeze. This is a nor'easter, so it's inverted from summertime. I think that's all I wanted to say about that.